Hi guys, welcome back to my channel, and this is the day 11 of IS bootcamp. And I'll be starting with the lead code problem, and the problem of the day is number of good leaf nodes pairs. And this question was asked in so many companies. I'll be showing what are all the companies, and meanwhile we can go through the question and then explanation will come to the noteboard. Okay. And you are given a root of a binary tree and an integer distance and a pair of two different leaf nodes of a binary tree is said to be good if the length of the shortest path between them is less than equal to the given distance. You have to return number of good pairs, leaf node pairs in the tree. Okay, basically here the given binary tree is given and the root will be given for the binary tree and the distance will be given, this ordered distance, and we have to calculate the leaf node. Here in case 4 is the leaf node and 3 is the leaf node, we have to find the distance should be less than equal to 3. Here 1 distance, 2 distance, 3 distance, all are unit distance, and 3 is less than equal to given target distance, so we have one pair. 4 and 3 combination will pair one pair. Only one good pair is there. And for this case here 4 and 5 leaves and 6 and 7 are leaves. And the distance is 3. If you calculate this shortest distance of 2 which is less than 3. One pair, second pair. This is also second pair. And if I calculate these two or any one from the left subtree and one from the right subtree, we will getting 4 because 1 2, 3, 4, 4 edges, which is exceeding the given target threshold. So we can't form one from the left subtree and one from the right subtree. The leaves are not possible. Only within the subtree we can able to do that. So only two pairs are valid, good pairs, and we can return. And for this also same. If I can convert this into graph, let me click on here. Yeah, this is the graph. If you see here, 6 is the leaf and 5 is the leaf and 2 is the leaf, and we have to form a pairs which is distance is less than 3. Let me check 3 is the distance, and let me check how what is the possibility. 1 2 3 4 here exceeding. If we connect it to, we are getting distance of 4 which is greater than 4 is greater than 3, so which is not possible. I have to check these two pairs. This is the possibility. See, 1 2 3, 3 distance for 5 and 2 if you connect 5 and 2 leaf pairs. So this is one of the possibility and we can return on this one. As you can see, 2 and 5 and 5 and 2, any one of them act as a good, only one valid good pair. And you can see that the number of nodes in a tree, the ranges from the 1 to 2 power 10, which lies inside the integer range only. And the node values, we know that range is 1 to 100 and distance is 10 power. Distance is nothing but maximum distance, how much depth of entry, nothing but a depth of entry is or ranges between 1 to 10, which means that we can go to the notepad. Here the same question is taken, and this question was asked in frequently. Let me take another letter. Yeah, this question was asked in TikTok 6 times, and last 6 months to 1 year it was asked in Josh Technologies. For 3 times it was repeated. For 1 and 2 years, within 2 years back, ByteDance and Google was asked. So this is very important for in terms of tree and converting to graph and finding the least common ancestors. Whenever the question comes, whenever question given to you from the individual side, have to think. We have to find the shortest path in a binary tree. Then we can simply say it was a LCA problem, least common ancestor, because when we want to find the least common ancestor for two leaf nodes, nothing but an LCA. Here, one is the LCA for this. So similar for 4 and 5, this is an LCA, shortest distance, which is nothing but least common ancestor. That is the main intuition of this problem. We have to convert, either we have to convert into LCA problem, or we can convert the given binary tree into graph, and you can do the traversal technique, and then you can solve any in anything BFS, using BFS or DFS approach, you can able to solve that. So let's deep dive the solutions. How many solutions we can come up? The distance is 10, right? The maximum height of the tree is 10. So which means that we have 2 power 9 possibility of leaf childs, which is nothing but 512 pairs we can form. On the left subtree we have 512. On the right subtree we have 512. So the combination is nothing but at worst case we can form of complete binary tree form of 512 square. Square indicates left and right multiplication. So this many combinations and time complexity will be number of nodes into 512. So that many pairs we can able to find, and we can able to find their lengths, so that we can check the condition whether the particular distance is matching within less than the given target distance. And the first approach using graph conversion, nothing but as I discussed, whenever this type of questions will ask, we have to convert into graph, and then with the help of graph, undirected should be, because we have to traverse. Why we are converting into graph? Because in a tree traversals we have three possible traversals. One is in order traversal, uh, pre-order traversals, and pre-order traversals, and post-order traversals. Post-order means left, right, and root, and in order is left, root, right. And in order is nothing but uh, pre-order, I said in order means first root and left and right. So these are possibles, and we can't go back to the parent directly. There is no access to go back to the parent in tree traversal. We have to convert into graph. That is the main uh, intuition of this problem. And you can see that same thing I have mentioned here. In the tree traversals, pre-order, in order, post-order, as I discussed before, and there is no direct access between parent and child relationship, and then we have to convert into the graph, unordered graph, and we can able to, with the help of unordered graph, we can traverse one node to any node with a direct access. And after converting into the tree to the graph, we can apply any graph traversal algorithms to find the shortest path between the leaves, and with the help of DFS or BFS we can able to solve. In this approach, I will be explaining BFS. And this is the question given, roots, and the distance is given. And I was taking unordered map and unordered set to store all the leaf nodes, so that on top of leaf nodes only we are using BFS. And this for the conversion of a graph tree to graph. And I was applying BFS function here to convert all the tree into graph. Here I was checking the current root node is not null. If it is null, we can return, we can stop here. If it is not null, we can add the leaf node if it is present. These two are base cases. And after that, we are checking for the previous node. Initially, I was passing null pointer because I was starting at a root. The previous node is nothing, so I was passing null pointer. So if the null pointer is if the previous node is valid, nothing, not a null pointer, then we can form an undirected graph like edges. Nothing but this is the root and this is the parent. I was linking bidirectionally. Root, parent to root and root to parent. Undirected graph here forming and storing in the graph. And after that, we are traversing left and right by passing current node left, which was coming from the ancestor of current, and same thing for the right traversing. And this is the DFS approach, and which follows post. I think this is in order traversal. First, I was checking for the route and then going for the left and right in order traversals, DFS, and then yeah, after converting that, we can use graph traversal algorithm, either BFS or TFS, and with the help of leaf nodes, as we are collected from here, and we are checking whether left is not null and right is not null, which means if it is both are null, there is no child to it, then we can act this as a child, and we can iterate through the all the leaf nodes which have the unique set of things. If it is contains duplicate, then we can avoid with the help of unordered set. And after traversing through the all the nodes within the given distance we are checking, and whenever we encounter the current leaf node, then we can store that. here distance I was going through, we have the target distance, and we are checking from 0 to distance, and checking for each level how many elements are there in the queue, and then we are popping out every element and checking whether the leaf node count, which is nothing but leaf node is exist. The current node should be exist in the leaf node. It should be an leaf node, and it should not be an the that other node is the current node and is a leaf node, and the leaf one should not be matched. So that two different leaf nodes we are checking, and we are incrementing the answer. Nothing but we found a pair because we are checking iterating through within the distance itself. That's the reason. And after that, we are using this condition to go through all its childs with the help of graph dot count of current node. If it contains any node, then we have some neighbors to it, and then we can use a set to its kind of an visited set. All the visited nodes it will be there, and we can avoid pruning. That's the reason we are using set visited set to avoid recomputing and retraversing the same node itself. So we are checking if it is not been visited, please push into the queue and mark it as visited. And after traversal, all the traversals, then this is comes and BFS, this entire loop, loop and for loops. And here visiting queue, we are pushing into the queue and then marking as visited. At the end, we will get pairs, right? We will get all the pairs count. So we want number of pairs, so that we are dividing by 2, so that we'll get a number of pairs out of. And after that, there is second approach will be using post order traversal. The main intention of this traversal is that if we want to find out the shortest path between any two nodes in a binary tree, then nothing but a finding of the LCM. And if LCA of two nodes is the deepest node, then the ancestor to the both XYZ utilize these insights. Nothing but ancestor will be the root of the XYZ child. So we can use shortest path between the leaf nodes and the traversing each node in the given tree, which means that here we have the root and we have children, and we are traversing every subtree and making the distance. For example, here for one distance we have one leaf node, and for two distance from here to here we have two leaf nodes. I think what this 8 and 9. Like this, we are maintaining the current state into the current node itself, and with the help of storing the sub-problem results inside one node, which is comes under institution of Fenwick trees and segment trees, where we are storing how many pre-computing and pre-processing and storing the current level, the current sub-problem results inside the one level, one node, current node itself. So that kind of an approach, it's a bit complicated, but it was more intuitive, and it is an institution that we can call the recursive function for the left subtree and find the distance associated there. For example, if you have the leaf node, the distance is 0 and one leaf node is there. For this, we have one distance of one leaf node, and for the two distance of two nodes we have. And coming to the algorithm, here the given question which was written in Java and previously I explained in C++. We are using post order traversals, like we are traversing all the leaf, and we are not missing out, we are not converting to the graph. That's the reason we will traverse from the left and right, traversing all the children first and then road, so that we can avoid coming back. After that, we are using post order traversals, and every time the current node is there and the distance is given, and checking if the current node is null, we can return and form up an array of 12 distances, like 12 distance, because we take 12. Initially questions state the distance will ranges up to 10 power 1 to 10, so we are taking some buffer one for the storing the results of one based indexing. So we have 11 indexes needed, and the 12th one will store the final answer. As you can see, 11th index will be storing the final index. After that, we are checking the node current node dot left and current node dot right is null. Both are null, which means it is a leaf node. For that leaf node, we can create an one array, current array of 12 indices, 12 size, and we can assign this the node distance of itself is 0, right? So we are assigning the current of 0 will be pointing to 1, and we can return that array. At the end, this particular will be written here, and it will pick the 11th index value, and we can return the number of pairs associated for that node. And we are using post order traversals, which means we should traverse left first, right first, storing the those values, and then this is the merging operation for the root node. For that, we are taking current array and combining the counts from the left and right subtree by shifting by one distance. Here we are taking additional array to convert into one based indexing and adding their sums and distance nothing but, and initializing the count, total count. By the 11th index, we should count all the left and right all the left trees and right subtrees stored in an answer, and we can iterate through the left node distance by using distance 0 to distance up to the target distance, and same thing for the polar, like we have to iterate through the leaf nodes, all the pairs. So we are adding pair 1 plus pair 2 within the given distance. Then we are adding the total number of good pairs to the final answer. Final answer will be stored at 11th index. So plus left of distance 1, right of distance 1. This is kind of a pre-processing computed results of left subtree and right subtree pairs, and compute it by multiplying and add it to the sum. The total distance is less than the given distance length. Here we are checking the condition, and we are multiplying the number of pairs and adding to the answer. And at the end, we can return that array, and it will pick the last index, 11th index. That is the where the value is stored. That's all. Yeah, that's all. Thanks.